Okay, so hello everyone. I'm Kailash Prasad, PhD scholar from Nano Electronic Devices and Circuit Lab. So we are here for live session 6, and this live session happens every Tuesday from 7 p.m. to 9 p.m. The course is Design and Analysis of VLSI Subsystem, and the course is taught by Professor Madhav. So we'll start. So this is the course layout as of now. What we have done, we have done till week 6. Okay, we have discussed about CMOS transistor and current model in the very first lecture, and then we have discussed about CMOS inverter. Then we discussed about noise margin, delay, RC delay, delay optimization, and combination circuit family. In today's lecture, my main goal is to discuss about the layouts, stick diagram, and interconnects. Okay, so we will try to have or discuss some of the questions on the layout. So what I have done, I have actually brought a new set of slides before teaching or discussing about layout. What I feel everybody should know this aspect. Okay, so if you have any doubts in that regards, please feel free to ask. Okay, so this slide is actually from microfabrication lecture, which is taught at in IIT Gandhinagar. So yeah, okay. So this lectures is actually taught by Professor Nihar Mahapatra at IIT Gandhinagar. So I have just borrowed his slides. Um because I wanted to show you, right? Because we are discussing about layout. How does this actually looks like? So whatever we'll be discussing will be in two dimension. But before that, we should visualize all of this in three dimension. Okay. So please note that this is the layout of a transistor. Okay. So this is what a transistor looks like when you take the transverse section of fabricated transistor, and all of this you can see over here. Can anybody tell me what are this? So this is the transistor you have. So these are nothing but metals. Okay, metals, wires, metal wires. Okay, so in any technology or in any technology, there are two things. One is transistors, right? So we have been discussing about transistor for quite some time, from 6 weeks. In this lecture we'll be discussing about transistor. Also along with that, we'll be discussing about interconnects, right? You can see over here that if you want to connect this transistor to say any other transistor sitting somewhere else, you have to go through this path or some path to connect it. Okay, you cannot directly connect it. You can connect via normal line in the schematic when you draw, but when you actually fabricate, you have to draw a metal line or metal wire. So it's a difficult task. Okay, so to explain it better, this is the slide where I'm showing the transistor schematic. So please note that this is an NMOS, this part is an NMOS. Okay, and this part is a PMOS. Okay, how do you identify? You can identify from the doping of the source and drain. Okay, this is how an NMOS and PMOS looks like. There is one thing you can see over here, okay, which is called as STI. We call this as shallow trench isolation. So this isolates NMOS and PMOS. So whenever we design a CMOS circuit, you might have seen that there are both NMOS and PMOS, equal number of NMOS and PMOS in the circuit. So whenever we design, we want to isolate, and this STI helps us in isolation. Okay, we will see how do we make this shallow trench isolation in a quick or very abstract level, such that you understand how the fabrication actually works. And this N plus or this NMOS actually sits on P well, where the substrate is P plus. Okay, and this PMOS actually sits on an N well, where the substrate is what we call as N plus. Okay, and you can see there are gates. Okay, and there are some spacer. We call this a spacer. What it does, it isolates the gate. You can see this gate and this contact from source and drain. Okay, there is an electrical isolation between them. Otherwise, this is also a polysilicon, this is a metal. If you don't isolate them, there can be a huge coupling between them, and yeah, short can also occur. So we put this kind of spacer there. Everybody know that okay, this is an oxide, because this whatever transistor we talk about is a metal oxide semiconductor transistor. Okay, and everything, all the NMOS and PMOS actually sits on a P substrate. Okay, so there is the P substrate. See, this is how a normal transistor schematic look like when you see from the transfer direction, right? Whatever layout we'll be making in the VLSI design course, we'll be seeing from top. What I'm showing you from the transfer direction, such that when you design from the top, you should have a slight idea that okay, if you are putting some layer, okay, how does it will actually look like when you will see from the transfer direction? Okay, any doubts till now? Any doubts?
No, no, we are good.
Assume no doubt, then yeah, we'll proceed ahead. Okay, so this is how a transistor layout looks like from top. Okay, so what we have seen, this is from the transfer direction, and this is from top. Okay, so this is the gate. Okay, you can see this is the gate. Okay, this is your source and drain. This is source, this part is drain. Okay, similarly for PMOS, there is a source, there is a drain. Okay, and there is a gate. Now you can see some square boxes over here. These square boxes, these are nothing but contacts, okay? Because you have to connect your source, drain, or gate, anything, to the upper metal layer, okay? So you have contacts, and any technology. This is a very important point. Any technology will have a contact of fixed size. Okay, fixed size. If you see any technology, you will have contacts which will be square boxes, but the sizes will be fixed. Okay, it can be zero point 0.8 cross zero point 0.8, zero point 0.9 cross zero point 0.9, or 0.10, 0.1 cross zero point 0.1. Okay, so this will be the size, right? What do you want when you design a circuit? You can what do you want? You want as many contacts as you can have over here. Okay, so in the given area, whatever the maximum number of contact you can get, you want that. And what is the reason behind that? The reason is very simple, right? If you have more contacts, more current can flow from the same area, from the same source or drain. Okay, otherwise what will happen, from a very smaller area, the current will flow, and it can happen that there is a very large power dissipation, and heating can happen. Okay, and it can damage your IC. So we want that okay, as many contacts as we can put, right? But you cannot put any arbitrary number of contacts, because it will be limited by whatever the width of the transistor you have. Along with that, between two contacts there should be some distance. Okay, some distance. Similarly, between contact and poly there should be some distance. All of these rules I'll be discussing later in the lecture. These are called nothing but as design rules. Okay, whenever you design a layout, you will have some design rules which are associated with it. So this is how transistor layout look like. Every transistor layout will have two things. One is layers, which we are drawing. So we are drawing these polygons, right? All of these are nothing but rectangular polygons. These are what we call as layers. And when we fabricate the layout, what happens is these polygons are actually converted into what we call as mask. Okay, if you have any fair idea how the fabrication works, so how does it work? So what happens? So whenever you want to say fabricate a gate, what we do, we have a mask. Okay, and when wherever the gate is, that part we will remove from there, and then we throw the light such that uh, uh, whatever the gate area we have, it gets softened such that we can have whatever gate we want to grow in that particular area. So that's how uh, actually the fabrication works, right? And this process is called what we call as lithography. Okay, so whatever layout you are making will actually be converted into this mask. Okay, this can happen that whatever mask you are designing, right? Either whenever you will sign the light, lithography is signing the light, right? Whenever you will sign the light, either that area get hardened, or it gets removed, right? It can be either way, right? So depending upon whatever the fabrication flow is, right, you do that. But the important thing is whatever layout you make will be eventually converted into this mask. Okay, and when And this is actually the most important process in every fabrication flow. Most important, okay? I'm not sure if you guys are following the news and all, right? So ASML is the company, which is a company based on Netherlands, and this company actually has a monopoly on this lithography tool, right? Because this lithography tool is the most expensive tool a fabrication facility has, right? Every foundry, let it be Intel, Samsung, TSMC, any company you name, this ASML provides a lithography tool. And what United States is trying to do is they have actually banned, they've asked ASML to not to supply to China, okay, such that they curb the Chinese manufacturing process. Okay, so that's the reason ASML becomes very important, because if you don't have the lithography tool, you cannot do any kind of application. Okay, coming back to our point, whatever layers we make, it will actually be converted into mask when we go to actual fabrication. Okay, so what are the layers we can draw? So these are a couple of the layers you should remember. The first is the active layer. Active area is the area where all the electrons will be flowing. Okay, we also call this layer as diffuser. Okay, this layer is the most important one, where all the electron flows, the channel form, the source drain are. Then we have N well, right? This and then we have gate. Then we have negative source drain. Then we have positive source drain. Okay, P plus and N plus. We can have contact metal one via one, metal two, then wire two, metal three via three, metal four, and then the final when you take the contact out from the chip and you can have a physical connection. Okay. Similarly, if you see yeah, this is the same slide, okay, where what are the mask you will require. So whatever the layers you will have, you will require that many masks to fabricate. So now, so this is a very detailed PPT. I'll be going in a very abstract level and just to make you understand, okay, how does a transistor is made. Okay, this is how a CMOS flow look like. The very first step in any CMOS flow is what we call as shallow trench isolation. Okay, shallow trench isolation means you design a oxide layer. So this is the oxide layer we are talking about. Okay, which will actually isolate NMOS and PMOS. Okay, why do you want to isolate NMOS and PMOS? Such that there is no crosstalk between them. Okay, uh, and how does it is made? So what we do, we have a silicon substrate. So this is the silicon substrate. We deposit the silicon dioxide. Okay, and then what we do, we put this Si3N4, and after that, using photolithography step, what we do, we try to remove this. Okay, so that this process is called as etching. After that, what we do, we deposit silicon dioxide over here. Okay, and this is a very pure oxide. After that, you deposit a large amount of oxide over here, and then what is the process we call as CMP. The process is called chemical mechanical polishing. So you polish the excess oxide you have and you remove this. Okay, finally you will have this beautiful looking shallow trench isolation. So that's the very first step. Okay, this is how it looks like. So this is the shallow trench isolation, right? And when you actually fabricate, so you don't have this beautiful square boxes, rather than you will have like this. Okay, so these are shallow trench isolation. That's the very first step. Now the any questions?
No, no, no.
Now the second step is you want to do well implant, right? So for NMOS you want a P well, and for PMOS you want an N well. Okay, how do you do that? So what you do, you because you will have so many shallow trench isolation, at least three, right? Because you want to both fabricate both PMOS and NMOS. Okay, you will cover one of the part and you dope in one of the parts. So this doping process is called as implantation. Okay, actual name is ion implantation, what we say. Okay, so the very first thing you will do, you will make a P type implant over here in this. Okay, you can see over here, and then you will cover this part, and then you will have N type implant over here, such that you will have what we call as P well and N well. Okay, so once you have that, this is how it looks like. You will do two things. The first one is oxide, because oxide is one of the important thing, right? the gate oxide we will deposit, which will be a very thin oxide. Then you will deposit gate, right? Now you can see over here both PMOS and NMOS has the common gate right now, but we want that, okay, gate should be isolated. Okay, so we should have individual gate, but you should understand when you are actually trying to fabricate, you deposit this polysilicon, right, throughout both NMOS and PMOS, and then later we differentiate. And how do you do that? This is how it will look like. You will actually remove this part, okay, this part also and this part also, right? This will be actually removed with the combination of two process, okay, photolithography, which I have already discussed, okay, which will be followed by etching. Etching means you put some chemical such that that part can be removed. Okay, so you call this as gate etching. Okay, so this is how now it will look like. Currently, what do we have? We have a well. Okay, that is my substrate both for NMOS and PMOS. We have oxide and we have polysilicon. Okay, now we require other things, which we call as my source and drain. Okay, source and drain. Now what we will do for PMOS, this is my PMOS. Okay, I will mask the PMOS. I will make the source and drain of NMOS. Okay, once you mask the PMOS, I will dope here. Okay, dope here N plus, here also N plus, and here also N plus. So when you do the doping, what will happen that along with the source and drain, your gate is also getting doped, right? And uh, eventually what you want your this gate should behave like a metal. Okay, this is because we call this as metal oxide semiconductor. Currently you had polysilicon, but once you have a very high doping, it will behave like a metal. Okay, so you will do that. You will have now source, drain, and you will have gate which is also doped. Similarly you will do for the PMOS also. Okay, and this is how it will look like. Okay, after that we actually put this spacer, right? We have already seen in the very one of the first slides that, okay, we want to isolate your gate and your source and drain contact. So you do that. After that, this is one more implant you will do for source and drain. Okay, and then the final process which comes is what we call as silicidation. Okay, so you want to make contacts, so this contact will be made using silicide. Okay, so using silicides we make the contacts in source, in drain, and sorry, in source, drain, and gate. Okay, source, drain, and source, drain, and gate. You do that. After that, so till now what we have done, we have actually covered the transistor part. Okay, you have actually fabricated a transistor. After that, what you want to do, you want to connect this transistor with many transistors. Okay, and you have to, whenever you want to connect one transistor with other, what you do, you put metal lines. Okay, and before that, before putting the first metal layer, what you do, you deposit the oxide, and this oxide deposition is called as what we call as ILD deposition. ILD means interlayer dielectric. Okay, ILD. Okay, you will deposit oxide over here. Okay, and then you can see we are actually pulling out contacts from source, drain, and gate. Once you do that, there are actually dedicated process for each of these. Okay, I'm not going into detail because this is not a microfabrication course, but the main goal behind showing you this is such that whenever I talk about, okay, this is my N well, okay, this is my P well, this is the gate, this is the contact, you should actually know, right, how in 3D it will look like, right? So the major goal behind behind showing this slides is that. Okay, so it will look like this. Okay, there is an NMOS, there is a PMOS, and then I have some context. Okay, this is some circuit. Okay, which we have done. I do not have put all the context over here, but some of the context. Now what we do, we go to the back end. In back end, what we have to do, we have to actually deposit your metal one. Okay, metal one. This is your context which is coming from, and this contact should be connected to metal one. Now this process is not an easy process. What we do, we have to make actually space over here, right? And then you have to make the contact. So there are a couple of layers which we use, and you do the cutting over here. Okay, and after that, what we do, once you have this, you will remove the third layer also, and you will put what we call as this titanium nitride and okay, titanium and titanium barrier, tante barrier, we say that. Okay, and then over that you put the copper. You might know that copper is the metal we use in the semiconductor, but you cannot directly use the copper, because if you directly put the copper here, copper can diffuse inside, and it will create problem for us. So we first put a barrier. Again, this barrier is also a metal, which is a costly one, so we put in a very little amount such that it stops, and then you put the copper, and after that you do the electroplating. Okay, you have the copper all over, right? This process which I have shown is called a single damascene process. single damascene Single damascene process to create this is the via. Okay, this is the metal. Okay, so it is connected through the drain of, yeah, or the source of the transistor. Okay, via, and then you have the metal, and finally you will have like this, and the final chip will look like this. Okay, I'm just showing you two transistors over here, but if you want to connect any of the gate of the transistor, you can see so many metal lines is going on, right? What we study is only this part, this particular part. Okay, but you should understand to have a or to define the characteristics of all the whatever chip you are designing. Along with this transistor, which is an extremely important thing, right, these interconnects are also important, because that if interconnects are not fast, okay, it is not carrying information correctly, then the overall chip slow down. So on and all, your performance, right, area, and your power, everything will be decided by both transistors and interconnects, right? So this was a very very quick, okay, I have actually covered in 15 minutes, right? It is a 2 hour lecture thing to be covered, but the thing is, whenever now I will talk about context, metal, active layer, NVL and PVL, you should actually able to visualize, okay, what layer I am talking to. Okay, and this is how in 3D your transistors look like. Any questions till now? Do you have questions? Did you understood?
Yes, sir. Alex, can you share this to us, like the slides? Is it possible to share to refer?
Slide, I will have to ask Professor Nihar, because I'm using his slide, but the video will be shared obviously. That if he allows, then I will share. Okay,
Okay, thank you.
right? Please understand this microfabrication, whatever I have taught, right? This is if you are preparing for any competitive exam, there is a separate section, at least two or three, one or two questions comes from this particular topic, whatever I have said, right? But my goal was not that. My goal was, before starting layout, you should actually know, okay, how the fabrication flow works, right? Now what we will do, we will go back to our actual lecture, which is this. Okay, so whenever we design the layout in of the CMOS, we follow what we call a stick diagram. Okay, you see, this is a stick diagram. Okay, for an NMOS and PMOS, right, which is connected to form an inverter. There are some notation. Metal 1 is generally been represented by blue color. Polysilicon is represented by red color. N plus diffusion is represented by green, and P plus diffusion is represented by brown color. And whenever there is a black cross, there is a contact. Okay. Uh, there are various ways by which you can make layouts, right? All of these are correct. Okay. What we will do, we will try to follow one of these nomenclature. Okay, so whenever I have to make this layout, right, I will make it for you. So you can see over here. So the very first thing what I have to do, I have to actually make the VDD. Okay, so for making the VDD, I think I will follow the color convention. Okay, this is my VDD and this is my ground. Okay, so you name it. VDD and ground. Okay. After that, the second thing what you have to do is you have to actually draw the diffuser. Okay, which is the active layer. So this is my diffusion. The upper one is for PMOS, the lower one is for NMOS. After that, what we will have is polysilicon. Okay, so I think I should have used a different color over there. Okay, so let me remove the colors. So the brown is for the upper diffusion, and the green is for the lower diffusion. Okay, so the brown is for PMOS and the green is for NMOS. Then what I will have is a poly. Okay, so this is my poly, right? So you see, when I draw the poly, okay, so wherever the poly and your diffusion crosses, it means there is a transistor. Okay, so this particular point, okay, so if I see over here, this is a transistor. Now it is connecting to P diffusion, so it is a PMOS, and this is an NMOS. Okay, so now we have made a transistor. Now what we have to do, we have to connect. And you see that the gate of both the transistors are connected. Okay, and along with that, what happens is the drain of both the transistors are also connected. Along with that, the VDD of PMOS is connected to VDD, and the source of the PMOS NMOS is connected to ground. Okay, so what I have to do is I have to make connections, right? I will make connections using blue metal line. Okay, so every time I make layout, I do some kind of nomenclature like source, drain, right, and source and drain. Yes, such that I should know, okay, what I am doing. So you see, the source of this transistor is connected to ground. So what I will do, I will make a connection like this. Okay, so the source is connected to ground. Now, source of this transistor is connected to VDD. So I will make a connection like this, such that, okay, the source of this transistor is connected. Now, if you see, the drains of both the transistors are connected. So these are the drain. Okay, so both the drains will be connected like this. Okay, and drain will give the output as Z, and gate, this is my gate, which will give the output as A. Okay, so this is how simple NMOS or simple inverter layout you will draw using a stick diagram. Is that clear, everybody?
Yes, sir.
So this is how it will look like in a much better manner. Okay. So if you want to draw NAND gate layout, right? Again, you will follow the similar approach. So I like this second one approach, right? What do you do? You have P plus diffusion, N plus diffusion, ground, and VDD. Okay. Now, if I just look this circuit and, okay, just assume that this is not here, right? Can I draw or redraw, okay, what layout it is? So if you want to do that, you have to see, okay, how many transistors do we have? So how many transistors we have? One, two, three, and four. Okay, so there are two transistors, which is two NMOS, and I have two PMOS, so that I know. Now what I have to do is I have to actually make the diagram from this. Okay, so whenever I want to make the diagram, I will see that, okay, how many transistors are connected to ground. Okay, you see, there is only one transistor, which is Q1, which is connected to ground. So I will make a transistor, okay, right, and I will connect this to ground. Okay, this is an NMOS because we know that. Okay, then this NMOS, right, uh, source is connected to ground, then it means that, okay, drain is connected to drain of the other NMOS. Okay, and its actually source is no. Okay, so if this is my source, this is my drain, I can have this source and this drain. Okay, so source is connected over here and drain is connected somewhere. So I have another transistor like this, right? So this drain, there is a source. Okay, there is a source and there is a drain. So this connection will actually mean like this. Then I will have another connection which is going up, which is connected to PMOS. Okay, so I have a PMOS, and you see over here the PMOS, one of the end of the PMOS is connected to VDD. Actually, both PMOS has one connection to VDD. That's how I understand it. Okay, there are two PMOSes, and both of them has one connection, so upper connection to VDD. And if you see the other connection of both of them is again shorted, right? So this connection is also same, and this connection is also sorted, and this is connected to the drain, right? So this connection is also sorted, and this is connected to drain, right? So this is how it looks like. So you can design the circuit using the layout, design the layout using the circuit. And if you have been given some layout, right, you should know how to build circuit out of it. Okay, any questions till now? Okay, no questions. So this is another circuit which I have given over here. Okay, so there is a homework assignment for you guys. What you do, you guys go and solve this and just make the layout. I have actually also put forward the solution, but you should not look into the solution. You should go and make the layout of this particular circuit, okay, from your own. Now, what I was discussing, what we call as design rules. Okay, so whenever we design layout, actual layout, right? When I'm talking about actual layout, it actually looks like this one. Okay, which is an actual layout, right? There is a rule between, okay, how much distance should be between the poly and the metal. Okay, how much distance should be between, actually minimum and maximum distance between the contacts, right? How much distance should be between p diffusion and n diffusion, right? Everything will have some rules associated with it, right? And these are called as design rules, and you can see, right? So there are rules for active, uh, how much maximum minimum width it can have. So this rule actually I have taken from Wester Harris book. Okay, CMOS Wester Harris book. So you can go to that book and you can understand the layout in a better manner, right? But the thing is, you will have some rules which are associated with it. Now, I have a question for you. Why these rules are there? Okay, why you cannot place two contacts very nearby? Somebody has made this rule, but what is the reason behind that? Can anybody tell me? Anyone? So I am repeating the question for you, right? So why these?
Sir, depending on the technology, this has to be followed so that no errors.
Because to estimate the delays and the channel length, so there should be the parameters, right? So based on the 65 nanometer, so we have some sort of rules and regulations.
So yeah, I know that there are rules and regulation. I'm actually questioning these rules itself, right? Why somebody is forcing me to do these rules? Why there are rules? Why I cannot have both metal lines actually very near together? Why I should have a distance of say 0.45 or whatever it is, or point 0.1? Any comments? Okay, so that's a very actually important question, right? Because we follow the rules, but we should understand why, from where these rules are coming from. So just to, yeah,
Sir, is this design rule is DRC
yes,
we do in cabinets?
yeah, it's the same, right? So DRC means design rule check. Okay,
Yes.
what are you checking? You are checking actually design rules. But the question is, I will go back to this slide to explain you why there are design rules, right? You see that you have made a very beautiful layout like this. Okay, you have made a very square layout like this. from top. But actually, when this contact will be fabricated, it will not look like this. It might look like something like this. Okay, something like maybe like this one. Okay, so it can happen. Why? Because whatever fabrication process we are currently using is not extremely accurate, right? You go to any technology, there will be a delta of a nanometer or two. Okay, although you have tried very beautiful layout in your Cadence or whatever tool you are using, Cadence Virtuoso or from the Synopsys design compiler or any tool. Okay, a custom compiler I'm seeing, right? You are making a very beautiful layout, but when it actually been fabricated, what happens that it can happen that the final will look like this, something like this, right? Something like this. And you can see over here, right, you have made like this, something like this. Okay, it has actually been made like this one. Okay, and you can see there are not sharp edges, there are actually curvy edges. Okay, so you see that okay, there is a delta between okay, what you are actually trying to fabricate and what actually being fabricated. Okay, and I'm just giving you a brief overview. Why does this happen? Because I have mentioned one of the steps, right? It is called as lithography, photolithography. And what you do, you actually for actually doing this etching, you will have a mask, right, which will be a perfect mask from you, and you throw the lights, right? What happens at the corner of this? So see, light will be coming perfectly like this, right? But at the corner of this, what can happen? The light can deflect, right? Light can deflect like this. So it can happen that okay, it will etch up to this like this instead of etching perfect perfect square or perfect rectangle. Okay, so this is not coming from design or anything else. This is actually coming from the fabrication or the tool itself. Okay, so that's the reason to make sure that whenever you fabricate, despite these variations, right, your actual layout should not. So what will happen that okay, I have made this layout, okay, like this, very beautiful one, and the other layout is very near by this. Okay, and when I fabricate, what happens that okay, this layout becomes like this, something like this. Okay, and this one also becomes like this, right? Now ideally you have placed it far apart such that okay, there is no electrical connection between them, but because of this fabrication process itself, what happened that okay, there is a short between these two, right? Now your logic has changed. You might have tried to design a NAND gate, it could become some other logic, right? Or it is just giving you 0 or just giving you 1, whatever the gate you have, right? And this thing is what we call as a very important thing in digital, analog, or any design we talk about. This thing is what we call as process variation. Okay, so whatever the steps we follow in order to fabricate all of these transistors or the entire chip, this is called as fabrication process. And due to this process, right, there can be some variations in the transistors itself, right? And this is called as process variation. Okay, so if you guys are have any hands-on on designing any digital circuits or any analog circuit, there is one step where every time, so if you want to say that okay, my circuit is working extremely correctly, there are actually three tests you have to do to make sure that okay, whatever circuit you are actually making is actually will be working in all the conditions. And these three tests are actually called as PVT. Okay, you should note down all of this whatever I'm saying, because these are very important points as a VLSI designer, right? And the first step is what we call as process variation. Okay, you have to test that okay, if there is process variation, if there is process variation in your circuit, still is your circuit is giving the required performance whatever we have designed. Okay, and in Cadence or any tool, there is one set of test or one set of simulation we do, and this simulation is famously called as Monte Carlo simulation. okay, in order to check whether your circuit is perfect, working correctly in under the process variation, right? So whenever you design any logic, whenever you design memory, whenever design you analog design, this one test has to be done, right? If you don't do this test and send for the fabrication, there's a very high chance that your chip might fail. Okay. Now the second test which I'm talking about is what we call as voltage variation. Okay. Ideally, I'm saying that okay, 65 nanometer technology has a voltage of 1.2 volt. Okay, very nice um, um, technology which has such a high voltage, right? Now, what happens that okay, you have given 1.2 volt, okay, and I have shown you, right? I have shown you this layouts. If you see over here, okay, I have given this 1.2, maybe somewhere, okay, somewhere here, somewhere, okay, I 1.2 is coming from some voltage source, right? But you see that okay, this if it 1.2 is coming here, this 1.2 is going through this metallic path, right? Now if you understand basic KCL and KVL, right, you will realize that okay, this is a metal wire. If you have a voltage which is passing through a metal wire, there is bound to be a drop across the metal wire, right? So and this 1.2 volt can vary, okay, depending upon what is the length of the wire. Apart from that, this metal is actually surrounded by oxide and are surrounded by another metal. So if you see that okay, there is a metal oxide metal capacitor is forming between these two, okay, and it can happen that okay, is there any change in one of the metals, it will impact the other of the metal, right? Because you know the basic behavior of capacitor. If there is a delta V over here, then delta V1 will be over here, right? So any change in the voltage will actually correspond to another change in the other terminal, because capacitance resist the change in the voltage difference, okay? So to maintain the voltage difference, it will also change, the other node will also change. So it can happen that okay, the voltage is also varying, okay. Ideally in all the chips the voltage variation is less than 5%, okay. So if your chip is working at say 1 volt, then there can be 50 millivolt process variation, okay. So sorry, voltage variation. So you have to make sure that okay, whatever circuit you are designing should work in this voltage variation, and you understand, right, from where this voltage variation is coming. This is actually coming from the layout and the source and the non-idealities over there, okay. So ideally you are focusing on this transistor, but because of this all these metal lines and all, it can happen that okay, whatever voltage you are supplying is actually not reaching to the transistors correctly, right? So you have to make sure that whatever circuit you are designing should work under this voltage variation. Now the third thing, and the actually one of the most important thing, is what we call as T, right? Anybody knows what the T means? I'm talking about process variation, voltage variation. Anybody know T?
Temperature.
This is one of the most important thing is the temperature variation. So you might have observed, right, if you have phones from uh, companies which are not high end, very high end, right? So which are under say 10,000 or so, right? If you go into, so I'm actually currently in Gujarat, right? Here the temperature goes to 47 degree in the summer, peak summer, and if you go to say Delhi, the temperature goes to 50 degree, right? And if you go to Sahara Desert or Thar Desert, right, the temperature can go to as high as 55 degree. Okay, so you, I don't know if you have observed, but I have observed that many of the phones, right, from I'm not naming the brand, but the thing is, many of the phones, right, which are not from the trustable companies, right, they actually hang whenever the temperature rises, right? As the temperature is also rising from the environment, and you will observe that your mobile is also getting hot, right, and it is getting hang. And similarly, if you go to say Leh Ladakh, right, and maybe Siachen, right, which is the coldest place in India, right, minus 50 degrees centigrade, you will observe that many of the mobiles will stop working, okay. So the thing is, why it is happening? Because all the characteristic of the transistor will also depends on the temperature, okay. So this is actually taught in electronic devices course, that okay, the charge carrier, the movement of the charge carrier actually depends on the temperature, right? So the thing is, whenever you are designing the circuit, you have to make sure that if the temperature rises, right, your transistor should work, right? What I have discussed is about the background temperature, but if you have observed that whenever you use your laptop or the thing, or your mobile, right, when you are using extensively, suppose you are playing a PUBG or maybe Call of Duty kind of game, right, your mobile get hot, right? So currently at that time the temperature of your laptop or mobile will be as high as 70 to 80 degree, right? But still your mobile or laptop is working, right? So you have to make sure that your chip, whatever you're designing, should work across the temperature. The standard range we follow as a circuit designer is from minus 40 degree centigrade to 125 degree centigrade, right? Your circuit should work across this voltage range, right? So whatever circuit you're designing, if you are a good designer, and whatever circuit you are designing should actually work in the process variation, the voltage variation, and the temperature variation. And if you can give me that, okay, whatever circuit you have designed works under all these three conditions, I will be very happy. Okay, provided it has the performance and the power benefit, right? So that's again the important parameter. But these are the three tests you have to do. Any questions in this?
Sir, how these temperatures were controlled?
Temperatures are controlled.
Um,
You mean that in a system which has a chip, how I control the temperature?
like how? What can I say?
Okay, you can repeat, right? Yeah.
Like if it exceeds the standard temperature, how it will control the system to come back?
Okay, so see, the thing is, if you have seen the advanced lighting systems, why our lab has very advanced lighting systems. Along with that, we have the supercomputing facility, Paramanand, sir, right? Wherever this computer sits, right, there is an extensive cooling system which is actually taking out all the heat.
Oh,
Whatever the system generates. So you are making sure that your system at not any time goes beyond the whatever the temperature range that has been given, right? So this extremely cooling system is one of very important thing. Various research are going on, but there are actually cooling that is seen in many of the mobile phones, not mobile phones, in laptops, right? You have this heating cooling feature which actually, and you might have seen the fans are there in the laptop, right?
to,
This constantly pulling all the heat.
yes.
Any more questions? Any more questions? We have only four students, right? You can ask question. We can have very heated discussions.
Sir, like DRC, we also have LVS.
Yeah, LVS is a different thing. Okay, so because you have pointed out this thing, I have actually this slide. So DRC is used to check all the design rules, right? Your layout is obeying all the design rules, and LVS is actually used. So whatever layout you are making, right? So suppose you have made this layout, okay, and you have made some schematic, okay, you will have this schematic, right? So whatever layout you are making, actually you have to make sure that, okay, layout and schematic are safe, right? Because here you are making electrical connection, and this LVS actually does that. LVS means layout versus schematic, okay? So if you have used cadence and all, whenever the LVS test pass, there is a smiley which comes, okay, yeah, like this, a smiley, right?
Yes.
So this is one of the happiest moment for a circuit designer when there is a smiley, right? So I give the assignments at here at IIT Gandhinagar, right? A very large layout design, and students get very happy and they put this smiley in their status, right? So that difficult actually passing the LVS is, right? But when you get expertise in it, you will eventually be a good designer, and at the very first go you can clear the LVS. Okay, so these are the two tests, and the tool we use, the standard industry standard tool is the caliber. This tool is from Siemens, or formerly known as Mentor Graphics. Okay, we use. Any questions? More questions? Okay, so if you do not have questions, then I have questions. Okay, so see, this maybe 50 minutes we have taken to understand the layout itself, right? And you might have seen how the layout actually looks in third dimension, how the layout looks from top, what are the things in the layout, right? When I'm talking about metal, maybe when I'm talking about diffusion, active, context, okay, where does it actually sits, right? We have seen couple of process like photolithography, okay, you have to cut down and you have to remove, and because of that, because of this all these steps, there can be variations in the circuit itself, right? And we call this as process variation. We have also seen, okay, there can be voltage and temperature variation. So whenever you design a circuit, it should actually be PVT tolerant. Okay, the process variation, voltage variation, and temperature variation, it should actually work in all these conditions. Whenever you will join any of the company, big companies, just like Synopsys, which is actually extensively working. Synopsys is extensively working in this memory design, SRAM memory design. When you go to say processor design companies like Intel, AMD, and mobile processor, right, Qualcomm, MediaTek, so their teams, if you will join, you will realize that okay, for a single chip, whatever process comes out, there will be maybe 1,000 to 2,000 tests which you have to run, right? At every corner, every possible corner cases you have to do, and then your chip will be gone for production. Okay, and making the design and the layout actually doesn't take much time, right? It takes, say, if it is taking 2 months, then the testing of the chip, checking everything is working or not across all the corners, all the PBT, all kind of inputs, if it is working on that, actually takes say 10 to 12 months, right? So the verification part is the biggest chunk of time consuming thing. Okay, so now coming back to the question we have discussed over here. So in a stick diagram, question is, in a stick diagram, which of the following statements are true? Okay, so you please tell me the answers. Which of the following lines are true? See, I have said, right, a polysilicon line, if it is actually on P diffusion, it will actually indicate a PMOS transistor. So this is a true statement. Okay, this is a polysilicon line. Okay, if this is a P diffusion, so this will be a PMOS, right? If it is an N diffusion, this will be an NMOS. Okay, polysilicon line on that. So this is wrong, but this is right. The lines of polysilicon and metal cannot cross over. So this is that. The diffusion lines are continuous without any break, and that is not true, right? We can have multiple transistors where there is no connection between the two, so there can be break in the diffusion line, right? So this is also not true. Okay, this is the, yeah, you want to say something?
No, sir.
The second point is, all the metal lines, when they are approximately the same width, they are actually the same width. Okay, so you have to make sure that uh, you are actually having the metal lines of the same width, right? So we assume that the metal lines are same width, but if required in the layout, you can change that. But in the stick diagram, actually, we make sure that, or we assume that all the metal lines of same width, and rest all the statements are actually incorrect. Okay, merge contact diffusion can be ignored in the estimating area. No. Uh, Stick diagrams are always drawn to scale. No, because these are not drawn to scale. And lambda based design rules don't apply when estimating area. No, when you are estimating the area, right, the lambda design rules actually apply. Okay, so when we have discussed about the lambda design rules, then okay, we have to see the the layout, and we will see that okay, how the lambda design rules will help us in deciding the area. Okay, so I have a compound gate a plus b dot c. Okay, and what I have to do, I have to estimate the area of this particular compound gate, and but before that, actually we have to make the layout of this compound gate. Okay, so this is a plus b dot c. Okay, so what I can do, I can have, so I will make the circuit for this. Okay, so this is A, B, and C. Okay, then A, B. Okay, this is my circuit. Okay, so AB multiplied by C, right? So the same is been shown over here. Okay, now what I have to do, I have to make the layout of it, or the stick diagram of it. Okay, so when you want to make the stick diagram, let us quickly make the stick diagram. So this is my VDD, this is my ground. Okay, the very first thing you have to do. The second thing you have to do is you have to make the P diffusion. Okay, then you have to make the N diffusion. So this is, okay, this is the N diffuser. After that, okay, whatever the number of gates you have, so you draw that many poly. Okay, so this is for A, then this is for B, and this is for C. Okay, so A, B, and C. Okay, now you see over here that I will use the blue metal line. Okay, so you see there that this particular C is connected to this node. So this is my Y. But what I've said, right? The very first thing you have to see that, okay, what are the transistors which are connected to ground? So there are two transistors which are connected to ground. Okay, A and B. So these are the two transistors A and B. Okay. So what I can do, I can make this is the common point which is connected to ground, right? So this is my source of both the transistors. So if this is my source of both the transistor, then this will be drain of both the transistor. Okay, so this is connected to ground. So but the thing is, drains are also connected. Okay, so then what you have to do, you have to make like something like this. Okay, something like this, then drains are also connected. Okay, after that, you see this node is actually connected to the source of C. So if you see the source, okay, the source is already connected. But if you see the drain, drain is connected to somewhere else. Where it is connected? A and C. Okay, so we will do that. But before that, what you can see that B and C, this B and C has a common connection of VDD. So you can make a common connection of VDD. Okay, so this is my uh, source of both the transistor. Okay, it is connected over here, right? And if you see the other connection, this one is actually connected to this C. So I will actually connect these two, right? And it is actually connected to source of A also. Okay, so I will make this as source. Okay, if I make this as drain, so if I see the B, so source is connected. Okay, so this is my drain. Okay, and then this is source and this is my drain. Okay, so okay, this is actually connected. These two node is actually been shown over here. Now this drain, this node will be connected to this particular place. Okay, so you will have Y from here, right? And let's see if there is any connection missing. We have all the connection, right? A, B, and C. So this is how A plus B dot C will look like. Okay, now whenever you want to estimate the area, right? So area will be, okay, height into width, height into width. Okay, whatever the height is and whatever the width is. So if you see over here that in the horizontal direction, how many metal tracks we have? This is the first metal track. Okay, then there we will have, okay, this is the second metal track, then this is the third metal track, and this is the fourth metal track. Okay, so four metal track across the width. Okay, and how many metal tracks we have here? One. Okay, two, right? And diffusion will have actually one metal track, and so both the diffusion will be considered in that. So this is three, this is four, and here it is five, and there it is six. Okay, so there are six metal tracks over here, right? Four, six into four tracks. Okay, so this will have six into four tracks, and actually whenever we use the lambda design rules, right, every track, we consider every track as, anybody know, in terms of lambda, every track width will be considered as how much lambda? Actually it is considered as 8 lambda. Okay, so it will be 48 lambda multiplied by 6 into 8, 48, 4 8 32, 32 lambda. Okay, so this will be 1536 lambda square. Okay, so this is the correct answer. Any questions in this? How I have made the layout and how I have calculated the approximated area using the lambda rules.
Sir, metal track, how did you take that?
So this comes under the lambda rules. Okay, so and, how many metal layers I have? So you are asking this or this one?
How did you consider that metal tracks?
Okay, how many metal tracks I have? So you are asking this, how I have considered it as six or four.
Yes, sir.
So if you see in the horizontal direction, okay, you ignore the poly part. Okay, you see one metal line is in there. Okay, there is another metal track. Okay, there is another metal track, and there is another metal track. Okay, so between every poly there are two metal tracks, and inside and outside of poly also there are two metal tracks. Okay, so from there I have actually considered four metal tracks like this. And how does this six comes? So six is coming from the height. So VDD and ground are two, right? Two diffusions are two more, two plus two, four. And you see there are two lines which are going. Okay, so these two lines. So again two, 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 two. That will be six. So
Okay, sir. Yes.
yeah, this is question two. Now quickly going to question three. Very easy question. The question here says that, okay, estimate the energy unit per unit length to send a bit of information, one rising and one falling transition. Okay, in a CMOS process with VDD is equal to 0.9 and capacitance is equal to 0.15 picofarad per millimeter square. Anybody knows what is the energy of wire formula? Anyone? You have given VDD, you have given the capacitance. What is the formula? Okay, the formula is CVDD square. Okay, we are actually considering both the transition. Okay, rising and falling. So that's the reason it is CVDD square. Otherwise, it would have been half CVDD square. Okay, so it will be 0.9 square into zero point 0.1. So this will be actually 0.81 into 0.15. And if I calculate it, uh, how much I will get? Anybody have the calculator? This will be, I guess, so 8 1 ja 8. Okay, point 0.1215 picojoule per bit per millimeter. Okay, so this will be the answer. This was a very simple question, formula based question we had. Okay, so if you have been given that, okay, this is the voltage and this is the capacitance associated with a metal wire, then okay, what will be the energy consumption? This will be the energy consumption. Okay, you can directly calculate. Moving to fourth question in this stick diagram, can you tell me what is the estimate area. I have already shown you, right, what is the estimated area. Now you have to tell me over here. I have given you the diagram. Tell me the estimated area. Can you tell me? Okay, so how many tracks are there in this direction? If you see from top to bottom, it is very simple. How many tracks? Anyone? You see how many horizontal lines? How many horizontal lines are there?
3.
Horizontal. One. This is one. This is two.
5.
This is three. This is four. This is five. But I have also said, right, you have to consider these two also. Okay, there are 7. And how many vertical lines are there? You have to ignore this poly, right? Apart from that, how many vertical lines are there?
9.
It's not 9. So you see, you have to consider this as 1.
5. Okay. Oh, 1, 2, 3. 5, sir.
5, right? So you have 1. This is 2. This is 3. This is 4. This is 5. Okay. But the thing is, if you see over here, okay, this particular case, although there is no line over here, okay, but still it will be considered in the area calculation. Why? Because there will be actually lambda design rule between these two. Okay, this is actually as same as whatever the metal line that you have. Okay. So basic idea of, okay, how many lines we will have, right? So okay, so this will be actually generally it happens that this is whatever the number of poly you have, right, plus one line you have, right? This is not true everywhere, but most of the time it happens like that. Okay, so in our case this will be 6, so 7 6 the 42. Okay, 42, and everything will be multiplied by 8 lambda, right? 7 lambda multiplied by, sorry, 7 into 8 lambda multiplied by 6 into 8 lambda. Okay, so if you multiply this, this will come as 2688 lambda. Did it?
Yes, sir.
Moving to next part, you can mute. So moving to next part, consider two inputs A and B. Okay, where B is applied to select line of 2:1 marks. Okay, so I am drawing a 2:1 marks. These are two. Okay, this is my select line. Okay, so 2:1 marks, right? 2:1. A bar is applied to I0. So this is my I0. This is my I1. This is applied as A bar. Input I1 is grounded. So this is 0, right? And you see in the select line, what is applied? B. What is the function? Can anybody tell me? What function this will implement? Anyone? Right. So what is the expression, Boolean expression for y? Y will be S bar I0 plus S I1. Okay. This is the Boolean expression. Now you put the values and tell me what will be the gate. Anyone? Yeah, please. Okay. So it is very simple. Okay. So see, S is B, right? So this will be B bar. I0 is A bar. Okay, then plus S is B and I1 is 0, right? So this is A bar multiplied by B bar, right? We can write using De Morgan's formula. So this will be A plus B bar, right? So this is A nor B, okay? A nor B. It was that simple. Okay, so you should actually have a practice of this kind of question. And why I'm saying that, okay, so this is one of the question that has been asked in my interview at here at IIT Gandhinagar. Okay, so the question was, okay, do you know that multiplexer is an universal gate, right? So my answer was yes, multiplexer is a universal gate, right? Now you can see that, right? Multiplexer has been used to design NOR, right? If NOR can be designed, any logic can be designed, right? Then the follow-up question was, okay, you draw multiplexer and design all the gates, okay, AND gate, OR gate, NOR gate, every gate, every possible gates, right? So it's a simple digital logic question, and if you are preparing for gate and all, okay, this kind of questions can come, right? In the interview, digital design interview questions, this kind of question can come. Okay, so by the way, interview was long time back in 2018. Okay, now moving to another question. uh, the question over here is the following propagation delay TPDF of transmission gate mux 2 is to 1 as compared to the rising propagation delay of the tri-stated inverter. Okay, so I will inverter based 2 is to 1 mux is okay. So this is an homework based question because I have given you two homeworks. Okay, what you have to do, you have to first design a 2 is to 1 mix, right? 2 is to 1 mux using TG transmission gate. Okay, then you have to design a 2 is to 1 mux using a tri-state inverter based logic. Okay, tri-state inverter based logic. Okay, so when I'm saying that, okay, you have to design 2 is to 1 mux, right? The Boolean logic will be y equal to s bar I0 plus s I1. Okay, this is the Boolean logic you are actually implementing, right? And then you figure out, okay, in terms of delay, how the things will be different. Okay, I have one more question for you for homework, right? So this is the gate because I have shown you using an I think it was a NAND gate, right? When I have a NAND gate, you can tell me, okay, what logic it is, right? If you have the layout. Now, if you have this layout, right, can you tell me what logic it is, right? What is the Boolean expression of it? Can anybody tell me? Will you be try to do if you will?
Sir, once repeat the question.
The question is, okay, this is the layout, right? Can you tell me what is the Boolean logic of this particular circuit? What I have implemented? Can you tell me the Boolean logic? You need to design a schematic of this. Others can also.
So I didn't look at it at all.
Sorry,
I think
you're not audible, right? What are you saying?
it's an adder circuit.
It's an adder circuit. Okay, so what will
Yes.
be the logic? So A XOR B XOR C, you're saying?
No, this G0, P1, P2.
No, the name is given over here, right? So is it an adder, right? So that might be misleading for you.
Full adder circuit.
Are you sure? This is a full adder circuit.
I'm not sure.
Because you are just telling the name of this, right? What you have to do, you have to go back in the home, right? And you have to design this circuit. And how do you design this? I will just give you a simple example. You take this node, right? This node is connected now in that circuit. Okay. So can you mute? I'm just clearing back my. So this is my ground. Okay. So this is my Z0. not G. So input is G0. Okay. Then if you see, there is another NMOS, but the one end of the NMOS is connected to this, the other end is connected to somewhere else, right? So it is like this. So this is my P1, okay, P1 input, right? Then you see this end, the other end of this particular yeah, this is also connected to ground. Okay, this node is also connected to ground, right? So if this kind of circuit we have, so we understand that okay, these two are in parallel. Okay, so G0 and P1. Okay, so these both are connected to ground, right? Then there is this node, right? So this particular node, right? You can see over here that this node is connected to some other logic, right? Some another NMOS. Okay, and if you see this NMOS, right? One end of this NMOS is connected to some logic. The other end of this NMOS is connected to my thing, right? So I will design this NMOS, okay? And this NMOS is okay. Sorry, I think I have made it wrong because I missed one of the transistors over here. Okay, so let me draw it again for you. So okay, this is my Z0. Okay, G0, which is connected to ground, right? This is my P1. This is my P1, right, which is connected. So this node is connected, right? This node is actually connected to another NMOS, which is connected to ground. So this is another NMOS, which is connected to ground. Okay, so this is how the logic looks like, right? And similarly, what you have to do is you have to design for so I have designed for this part, and this part, right? When you design for this particular all the four, right, you will have the entire pull down network PDN. Okay, then correspondingly you go up, you design all the network, and then you will have a logic of Y, right? What will be the final output of Y? Okay, so this circuit, this expression you have to find out, right? If I have to quickly write this particular expression, this is nothing but P1 G0 plus G1. Okay, so at least I know that okay, one part of the circuit is P1 G0 plus G1. Okay, similarly, what you have to do, you have to go back and you design the circuit. Try to do today itself this particular circuit, right? And in the WhatsApp group, maybe you post the solution, right? What solution you are getting, uh, such that at least I know that okay, whatever I am teaching over here, right? You guys are understanding, and whatever Professor Madhav Rao is teaching, you guys are understanding. Okay, so today's class will be over here, right? So this was my last slide. Okay, if you have any queries, feel free to ask.
So you told WhatsApp group.
You do not have the link of the WhatsApp group?
No, sir.
Just give me a minute. Okay, so in the chat box, I have actually shared the WhatsApp link. You can join using this link.
Okay, sir.
So the WhatsApp group can be used to ask questions. Any question you feel free to ask over there. So if you guys have no question, then I will sign off. Thank you for joining. We will meet again in the next session. Okay. So please encourage other students also to join this session, right? Because we are actually, I'm trying to discuss many of the things which are not trivial to us, right? And many of the concepts that it will help you understand things in the future. Thank you. Thanks for joining.
Thank you, sir.